Hello, my full name is Kopbay and I'm a PhD student and junior researcher at Al-Farabi Kazakh National University. The title of our article is Design and Simulation of Rectangular Patch Antenna Arrays with High Bandwidth for 2.4 GHz ISM band applications. At the current time, research on microstrip patch antennas continues to progress, mainly due to their small size, affordable cost, and easy production. This paper presents a flexible patch antenna array design to address common bandwidth challenges in the 2.4 GHz ISM band, where bandwidth tends to be narrow. We developed and analyzed 2, 4, and 8-element rectangular PAA patch antenna array configurations using a quarter-wave transformer and parallel connection method for patch links. Simulations were conducted in Ansys HFSS to fine-tune antenna parameters and achieve the best MPA design. Our findings show promising bandwidth improvements with 4 and 8-element PAAs, reaching bandwidth of 290 MHz and 210 MHz, which are 8.75 and 12% of their total capacity. We also observed ideal impedance matching with return losses S11 of minus 51 dB for single patch and minus 37.5 dB for the 8-element array. Notably, the 8-element performed exceptionally well, achieving a gain of 9.70 dB and directivity of 13 dBi, and also VSWR below 0.5, ensuring strong signal transmission and reception. In wireless communications, the need for compact and efficient antenna design is critical. Microstrip patch antennas are popular due to their small size, ease of production, frequency flexibility, and ability to integrate with various devices. While MPA, its microstrip patch antenna, offer many benefits, they often have limited bandwidth, low gain, and may require improved directivity for certain uses. Different patch shapes like rectangular, circular, and more complex designs have been explored to meet specific requirements. Building a patch antenna array introduces additional challenges, especially in optimizing performance by carefully adjusting the geometry and spacing between elements to achieve ideal bandwidth, directivity, and side lobe control. The size and shape, feeding techniques, and substrate material are very important in antenna design. For example, in many works, researchers often select material, often select different feeding methods based on their suitability for specific applications. In our design, we choose the edge feed with a corporate network due to its simplicity, ease of integration, and scalability. This study focuses on creating and evaluating an optimized, simplified design for a rectangular microstrip patch antenna array to enhance bandwidth gain and to achieve an ideal impedance matching using the cost-effective FR4 epoxy material. We present the best performing designs of the single patch antenna model along with 2, 4, and 8 element patch antenna array configurations, achieving good results such as 290 MHz bandwidth and a return loss up to minus 30 dB. These designs were developed in the HFSS Ansys environment with an operating frequency of 2.4 GHz, which is widely used in ISM applications for wireless communication. FR4 epoxy was chosen over alternatives like Rogers or RT Duroid due to its affordability and cost effectiveness. Also for good mechanical properties, making it ideal for various electronic applications. About methods, to develop the optimal MPA design, patch dimensions, substrate material, and operating frequency should be defined. The width and length of the patch antenna is a key parameter that influences its radiation pattern, impedance matching, resonance frequency, and so on. The equation that we use for calculating patch width is presented in equation 1, where c is the velocity of light, fr antenna's resonance frequency, er its substrate dielectric permittivity. In MPA, the width of the patch is typically chosen to be a fraction of the guided wavelengths to manage its resistance. The the wavelengths, guided wavelengths of a patch antenna denotes the wavelengths of the electromagnetic wave guided along the microstrip transmission line formed by the patch and the ground plane. It depends on the effective dielectric constant, E effective, of the substrate material and the operating frequency, and it is usually shorter than the free space wavelengths due to the dielectric properties of the substrate. It's shown in Formula 2. The effective dielectric constant, EF, considers how the substrate material and the geometry of the patch affects the electrical characteristics of the antenna. In order to calculate it, we use an empirical equation 3, where h, the substrate material height, and the length of the patch is given by formula 4. However, as radiation doesn't emanate from the center, but rather from the region between the edge of the patch and the grounded surface, the phenomenon referred to as the fringing effect arises. Consequently, electrically, the patch appears longer than its typically calculated length, giving rise to the concept of delta L, which represents the extra electrical length. It's shown in figure 1. The equation 5 represents a widely used and pragmatic approximate relationship for the normalized length elongation. Then we can calculate the effective length of the patch denoted as L effective, as in equation 6. Also, we use equation 7 for calculating the dimensions of the grounding surface and substrate size. And the next stage is to define the size of feeding mechanism. For example, in our work, we use edge fit, where quarter wave transformers should be used. Feeding mechanisms are used to transfer electromagnetic power from transmission line to the antenna by transforming energy into electromagnetic radiation. It plays a critical role in impedance matching and effects on basic characteristics such as radiation pattern, frequency, and polarization. Common types of feeding mechanism in patch antenna include microstrip feed, proximity feed, aperture-coupled feed, and coplanar waveguide feed. In this article, the microstrip edge feed was favored for its design simplicity and ease fabrication, which involves connecting a microstrip transmission line directly to the edge of the patch antenna. With any feeding technique, achieving accurate impedance matching is vital as it minimizes signal reflections and standing waves while maximizing the power transfer efficiency. Impedance matching flexibility can be achieved by varying the width and length of the transmission line. We have determined the width and length of the patch by these equations. In order to define and calculate the feeding size, it's necessary to determine the load impedance ZL of the patch through the equation 8. Thus, when substituting values into equation 8, load impedance is approximately equal to 285 ohm, and provided that the characteristic impedance that zero is 50 ohms, there is a great, we can say that there is a great impedance mismatching, and it can be checked by calculating the reflection coefficient. So ideal matching is characterized by a reflection coefficient close to zero. To minimize the reflection coefficient, we employ matching technique as quarter wave transformer, which alter the impedance of the antenna to align with the characteristic impedance of the feeding transmission line. This approach adjusts the phase and magnitude of the reflected signal to diminish the reflection coefficient. To calculate quarter wave transformer impedance, we will use equation 9. The length of quarter wave transformer is equal to lambda divided by 4, and it can be seen from figure 2. The width of the quarter wave transformer and microstrip fit with a characteristic impedance of 50 ohm can be determined using the equation 10. And the table 1 displays precise width and length dimensions of all parameters for modeling the corresponding SPA type discussed in this article. Given that the above-mentioned equations are based on empirical observations, it's required to adjust some parameters to align with the model, potentially resulting in slight variations of certain values. In this paper, we have gathered PAA patch antenna array of varying configurations, including 2, 4, and 8 elements to ensure a more equitable comparison of the results. Each individual patch dimensions coincide with the data indicated in table 1. It can be seen from figure 4a. The wavelength between the patches is divided into fractions equal to lambda divided by 6, lambda divided by 4, and lambda divided by 2. The width and length of matching network transforms presented in table 2. When constructing a 4-element PAA, the identical circuit is used as in a 2-element PAA. Two similar patches are added in parallel, which are located at a distance of 48.7 millimeter. And spacing between patches is determined based on the guided wavelength, which is equal to 59.1 millimeter. In order to improve the characteristics of the antenna array, the distance between the two upper and lower antennas should be made less than the wavelengths. In this case, it's equal to 0.82 guided wavelengths. The radiation elements are excited using a shared feed line, ensuring uniform power distribution between them. The same steps are performed when creating an 8-element PAA in order to connect two sides of an array consisting of 4 elements. We need to use conductor line with a length of 2 guided wavelengths. So the simulation are shown in figure 4 was proposed. SPA and PAA was carried out by software product for electrodynamic 3D model, Ansys HFSS. The operating frequency of the antenna is chosen to be 2.4 GHz. The substrate is FR4 epoxy with dielectric permittivity, which is equal to 4.4. Following that, we compare the simulation results of all patch antenna arrays, namely parameters as return loss, bandwidth, gain, VSWR, voltage sending wave ratio, directivity, and radiation patterns. In the realm of antenna engineering, the S11 value is crucial metric as it quantifies how effectively the antenna converts incoming signal energy into radiated waves, and Lower values of S11 denote superior impedance matching between the antenna and its transmission line, translating to reduced signal loss and enhanced overall performance. As depicted in Figure 5a, the S11 parameter of SPA reached the highest point at S minus 51.7 dB. And similarly, S11 results do not differ significantly in the two-element PAA Figure 5b, achieving minus 47.5 dB. Both types of antennas have a bandwidth of 60 MHz. Subsequently, by utilizing a parallel patch addition scheme and optimizing patch placements based on a model, a four-element PAA attained bandwidth 290 MHz and at minus 10 dB, with an increased number of resonant frequencies observed at 2.28, 2.39, and 2.49 GHz. In the 8-element PAA, there are also multiple resonant frequencies, as illustrated in Figure 5D, where S11 reaches minus 37.3 dB, and there is two resonant frequencies. The bandwidth covers total 208 megahertz bandwidth. We have compared these results with other works and realized that the values of bandwidth, S11 parameter, and VSR are very good, which shows an ideal impedance matching. The next parameter is the antenna gain. The antenna gain is one of the most significant key components to describe how the radiation pattern of the antenna is concentrated, and combines the directivity and the efficiency of the antenna into one easy-to-use parameter. In order to see the full picture of the received data, we use the radiation pattern extracted through far-field analysis in Ansys HFSS. We obtained 3D models of gain encompassing azimuth angle values ranging from minus 180 to 180 degree, and elevation angle theta values ranging from 0 to 360 degree. The 3D radiation pattern of SPA exhibits a uniformly round distribution, which suggests symmetrical radiation characteristics with minimal variation in intensity around the antenna's axis. The gain and directivity value of SPA reached 2.64 dB and 5.96 dBi of directivity, respectively. In the case of two-element PAA configuration, we obtained a substantially strong gain of 6.03 dB and directivity of 8.8 dBi. From the given three-dimensional radiation pattern in Figure 6b, it can be seen that even in the back lobe there is a certain level of radiation intensity. Furthermore, the gain has increased to 7.08 dB for the four-element patch antenna array, and to 9.70 dB for the 8-element patch antenna array. It is shown in Figure 5, C and D. Using a 3D polar plot, we can visualize how the antenna emits beams in 3D space, whereas a 2D plot is useful for accurately defining directivity and angles of emission, since it represents a cross-section of the 3D pattern. The 2D radiation pattern of the SPA is characterized by a half-power beamwidth HPBV of 83 degree. It's shown in Figure 7a, indicating the angular span within which the radiation intensity drops to half minus 3 dB. In the two-element patch antenna array scenario, the 2D plot demonstrates an even gain distribution and wide radiation angle, similar to SPA, with HPBV value spanning 88 degree from minus 40 and to 49 degree. Additionally, a more pronounced side lobe and back lobe was observed from the H-plane in the two-element PAA. And it can be noticed that the H-plane in each plot has a similar trend, where increasing the number of patches leads to a reduction in the width of the main lobe and the appearance of additional side lobes. For 4-element and 8-element PAA configurations, the E-plane exhibits a more focused main lobe with HPBV of 52 degree, ranging from minus 5 to 57 and 61, spanning from and 61 spanning from 4 degree to 65 degree respectively. It's shown in figure 7 C and D. All the data acquired during the modeling, including gain, return loss, VSWR, directivity, and other parameters, are shown in Table 3. The animation of how electric field strength is propagated through the media in 8-element patch antenna array is presented in Figure 7. As can be seen, the surface current is uniformly propagated in two directions from the lower side of the patch antenna. However, there is a slight phase shift between the upper and lower groups of patches. So to conclude, this study introduced a simple effective design for a rectangular patch antenna array with 2, 4, and 8-element configurations optimized for the 2.4 GHz ISM band. To achieve this, a quarter wave transformer and parallel addition scheme were employed with an edge feeding technique. This approach resulted in a significant bandwidth increase of 290 MHz, representing 12 of the total bandwidth. 12% of the total bandwidth. Simulation results show that the proposed design achieved impressive values with a return loss of minus 37.3 dB and VSWR of 0.23, indicating excellent impedance matching. The highest gain and directivity recorded were minus 9.70 dB and 13 dBi respectively for the 8-element PAA configuration. Analysis of the 2D and 3D radiation patterns confirmed that directivity improves as more patch elements are added. This PAA design is easy to integrate and well suited for various wireless communication systems. Thank you for your attention.